Have you ever gazed up at the night sky and wondered what holds it all together? What is the invisible fabric that connects the stars, the planets, and everything you see? This cosmic tapestry is what scientists call spacetime, a concept so profound it completely changed our understanding of the universe. It's not just empty space. It's a dynamic, four-dimensional structure that bends, twists, and ripples. Imagine a vast, stretched-out trampoline. This is our spacetime. Now, place a bowling ball in the center. See how it creates a dip, a curve in the fabric? This is exactly what massive objects, like stars and planets, do to spacetime. This simple analogy is the heart of Albert Einstein's theory of general relativity, published over a century ago. He proposed that gravity isn't a mysterious force pulling objects together, but rather the effect of mass and energy curving the fabric of spacetime itself. Objects moving nearby, like a marble rolling past the bowling ball, don't get pulled by the ball directly. Instead, they follow the curve created by the ball in the trampoline. This is how planets orbit the sun. They are simply following the straightest possible path through the curved spacetime created by the sun's immense mass. For decades, this was a brilliant but theoretical idea. We could see its effects, like the precise orbit of Mercury, which Newton's laws couldn't fully explain, but Einstein's theory nailed perfectly. But how could we prove spacetime was a real physical fabric? The proof came in the form of ripples, tiny vibrations in the fabric of spacetime itself. Einstein predicted these ripples, which he called gravitational waves, would be created by the most violent and energetic events in the cosmos. Imagine two massive cosmic objects, like two black holes, locked in a spiraling dance. As they orbit each other faster and faster, they churn the spacetime around them, sending out waves of gravitational energy that travel across the universe at the speed of light. These waves are incredibly faint. By the time they reach Earth, the distortion they cause in spacetime is smaller than the width of a proton. Detecting such a minuscule change seemed like an impossible task for a very long time. But humanity is persistent. Scientists built an incredible machine called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two identical detectors, thousands of kilometers apart, each with two long arms forming an L shape. Inside these arms, laser beams are shot back and forth, bouncing off mirrors. Normally, these laser beams are perfectly in sync. But if a gravitational wave passes through Earth, it will momentarily stretch and squeeze spacetime itself. This stretching and squeezing would cause one of LIGO's arms to become slightly longer and the other slightly shorter for a fraction of a second. This tiny change would knock the laser beams out of sync, creating a specific signal, the chirp of a cosmic collision. On September 14, 2015, it finally happened. For the first time in history, LIGO detected the distinct chirp of two black holes merging, an event that had occurred over 1 billion years ago. The signal was a perfect match for the predictions of Einstein's theory. This discovery was monumental. It was the first direct observation of gravitational waves, and the first time we had heard the universe in this new way. It was irrefutable proof that spacetime is a real physical fabric that can be disturbed. Since that first detection, LIGO and its partner observatory, Virgo, have detected a large number of gravitational wave events. These events are opening a new window into the universe, allowing us to observe phenomena that are invisible to traditional telescopes, like the collision of neutron stars. But if spacetime is a fabric, what is it woven from? What are the fundamental threads of this cosmic material? This is where modern physics ventures into the unknown, to the very edge of our understanding. One of the leading ideas attempting to answer this question is a branch of theoretical physics called quantum gravity. Its goal is to unite two of our most successful theories, Einstein's general relativity, which describes the large-scale universe, and quantum mechanics, which describes the tiny world of particles. These two theories work perfectly in their own domains, but they clash when we try to describe situations where both extreme gravity and quantum effects are important, such as at the center of a black hole or at the very beginning of the universe during the Big Bang. One of the most prominent approaches to quantum gravity is string theory. It suggests that the fundamental constituents of the universe are not point-like particles, but unimaginably small, one-dimensional vibrating strings of energy. According to this theory, everything we see, electrons, photons, quarks, are just different vibrational modes of these fundamental strings. Much like different notes played on a violin string correspond to different frequencies. In this framework, space-time itself is not fundamental. Instead, it emerges from the complex interactions and collective behavior of these countless vibrating strings. It's like how the properties of water, like wetness and fluidity, emerge from the interactions of individual H2O molecules. Another fascinating idea is called loop quantum gravity. This theory takes a different approach. It proposes that space-time is not a smooth, continuous fabric at all. Instead, it is made of discrete, indivisible units, or quanta, of space and time. Imagine the fabric of a T-shirt. From a distance, it looks smooth and continuous. But if you look very closely with a magnifying glass, you can see that it's actually woven from individual threads and loops. Loop quantum gravity suggests that space-time is similar. If you could zoom in to the smallest possible scale, known as the Planck length, a scale trillions of times smaller than an atom, you would see that space-time is made of a network of interconnected loops. These loops form what physicists call a spin network. In this picture, space is not empty. It is a granular structure, and time doesn't flow smoothly. It ticks forward in discrete, indivisible steps. The universe, at its most fundamental level, is a quantum network of information. Both string theory and loop quantum gravity are still theoretical frameworks. We do not yet have the experimental technology to probe spacetime at such incredibly small scales to prove or disprove them. They are mathematical constructs that offer tantalizing glimpses into the nature of reality. So, the search for the ultimate fabric of the universe continues. We know from Einstein and LEGO that spacetime is a real dynamic entity. It curves, it ripples, and it guides the dance of galaxies. But its fundamental nature, its quantum threads, remains one of the greatest mysteries in all of science. Are we living in a universe woven from tiny vibrating strings? Or is reality a granular network of spacetime quanta? Perhaps the answer is something else entirely, a concept so strange and new that we haven't even imagined it yet. Every gravitational wave we detect, every new theoretical model we build, brings us one step closer to understanding the ultimate secrets of spacetime. The journey to understand this cosmic fabric is a journey to understand our place in the cosmos. It's a testament to human curiosity, pushing the boundaries of knowledge to answer the most fundamental question of all: what is our universe made of? Thank you for joining us on this journey through the fabric of the cosmos. To explore more mysteries of the universe, be sure to subscribe to Space Repo.